Last lecture we drew the Bode magnitude, factor decomposition, sum of dB asymptotes, 3 lines, and you are done. Today, the second half of the Bode plot, the phase. Same factoring trick, different rules, same speed. Why phases add? The angle of a product equals the sum of the angles. Angle of G times H is angle of G plus angle of H. So when we factor a transfer function into atoms, the total phase is the sum of each atom's phase contribution. And division flips the sign. Angle of 1 over G is minus angle of G. So a denominator factor like 1 over S plus a contributes minus its phase, while a numerator factor like S plus a contributes plus its phase. Mirror images. Just like with magnitude, we get a sum of asymptotes, only this time the asymptotes live on a phase axis marked in degrees. Phase rules per atom. Constant K. Phase is 0 degrees if K is positive, plus or minus 180 degrees if K is negative. A flat horizontal line. Integrator 1 over S. Phase is constant minus 90 degrees at every frequency. Differentiator S plus 90 degrees. An n-fold integrator 1 over S to the n contributes minus 90 n degrees. Pure constant offsets. Simple pole 1 over S plus A. Phase is 0 below the corner, minus 90 above the corner. The transition is smooth, centered at the corner. Simple 0 S plus A. Mirror image, 0 below plus 90 above. Right half plane 0, S minus A with positive A. Same magnitude behavior as a left half plane 0, but the phase goes minus 90 instead of plus 90. This is the non-minimum phase signature. Physically, it produces undershoot in step response. We will revisit this in compensator design. Complex conjugate pair. Phase rotates twice as fast. 0 below the natural frequency, minus 180 above, with a steep transition controlled by the damping ratio. The decade rule. For a simple pole or 0 with corner at omega equals A, the asymptotic phase transition can be drawn as 3 line segments. First, flat asymptote at 0, holding for omega less than A divided by 10. Second, a straight ramp from 0 to plus or minus 90 degrees between omega equals A divided by 10 and omega equals 10 times A. The slope of this ramp is plus or minus 45 degrees per decade. Third, flat asymptote at the limit value, plus or minus 90 degrees for omega greater than 10 times A. At the corner omega equals A exactly, the phase is plus or minus 45 degrees, halfway through the ramp. Useful checkpoints. 1 decade below corner, phase is roughly 5% of the limit. 1 decade above, roughly 95%. Between, the ramp is the asymptote. Worked example. Same transfer function from last lecture. G of S equals 10 divided by S times S plus 1 times S plus 10. Atoms. Constant 10. Positive. Contributes 0 degrees. Integrator 1 over S contributes minus 90 degrees, flat across all frequencies. 2 simple poles, corner at 1 and corner at 10, each contributing a transition from 0 to minus 90 degrees, with the decade rule centered on its corner. Total. Below omega equals 0.1, the phase is just the integrator contribution, minus 90 degrees. Between 0.1 and 1, the first pole's transition starts. Phase ramps down from minus 90 toward minus 135 degrees by omega equals 1. Between 1 and 10, the first pole completes its drop and the second pole's transition begins. The total phase reaches minus 180 around omega equals 3 or so, then continues toward minus 225 degrees by omega equals 10. Above omega equals 100, Both poles are deep in their asymptotic regime. The phase settles at -270 degrees, -90 from the integrator, -90 from each pole, totaling -270. How accurate is the asymptotic phase? Quite accurate, but a bit looser than magnitude. The actual phase curve is smooth, and the deviation from the straight line ramps can reach about 6 degrees at the kink points, where the ramp meets the flat asymptote. For complex conjugate pairs with low damping, the deviation can be much larger near the natural frequency. The phase swings rapidly through 180 degrees in a narrow band. For most engineering work, choosing a controller, finding gain crossover frequency, reading phase margin, the asymptotic phase plot is more than enough. One application worth previewing. At the gain crossover frequency, where the magnitude curve crosses 0 dB, the phase tells us how close to instability the closed loop is. If phase at gain crossover is, say, -150 degrees, the phase margin is 180 minus 150 equals 30 degrees. A small margin, the system is lightly damped, prone to overshoot. If phase at gain crossover is closer to -180, the margin shrinks towards 0, and the closed loop teeters on instability. We will dig into gain and phase margins in 2 lectures. For now, remember, a Bode phase plot is not just decorative. It tells you, at every frequency, how stable a closed-loop system designed around that loop gain will be. Summary. Bode phase plot. Phase in degrees versus log frequency. Total phase is the sum of factor phases. Use the same atom decomposition as for magnitude. Each atom has a known asymptotic phase, 0 or 180 for constants, plus or minus 90 for integrators and differentiators, smooth transition between 0 and plus or minus 90 per simple pole or 0, double for complex pairs. Decade rule. Simple pole or 0 ramps over 2 decades with the corner at the midpoint. Sum the contributions, draw the curve, read the system. With magnitude and phase, the Bode plot is complete. Next lecture we do a few full Bode examples, magnitude and phase together, and start to read what they tell us about stability and bandwidth.